start the recording. So thank you everybody for joining AppSec Australia. And today we are very lucky to have Professor Ron Steinfeld from Monash University. He's going to give us an overview of quantum safe cryptography. This is going to be so important because cryptography is going to be going through some changes, and the algorithms we know like RSA and Diffie-Hellman might eventually be phased out. So to keep your knowledge up to date, I think this talk is especially important. Ron is a professor, associate professor at Monash University. He's internationally known for his research on lattice cryptography, quantum safe cryptography. He has over 80 publications. He's been doing research for more than 20 years, and he won the Best Paper Award at ASIACRYPT 2015. He's got so many other accolades. I can't list them all, but that's briefly it. So Ron, happy for you to take over when you're ready. Thank you for joining.
Yeah, thank you very much, Scott. I'm very happy to join you today and talk to you about my research area and some of the things that's been happening in this field. So I'll start by giving a description of the topics I'll cover. Basically, I'll start by introducing the threat that is posed by quantum computing to the currently deployed cryptography that we have in all our software today. And hopefully this will motivate the rest of the talk about why we need this quantum safe crypto that I'll be talking about. And then I'll tell you what quantum safe crypto solutions and approaches that we have at the moment. So I'll keep the description at a very high level, so I won't go into all the math, although it's very interesting and beautiful. But I want to keep the talk accessible, so I will not get into a lot of the details, but I hope to give you some idea of kind of the history and also some of the performance and security aspects of these algorithms, and also what is coming in the near future with the new crypto standards, quantum safe standards that are being prepared by organizations like NIST and ETSI. And then I'll finish up by looking at very quickly at some of the current existing research topics in this area and the challenges that we are working on in that domain. All right, so that's the plan. So I think I can start by telling you a little bit about quantum computing. So you may know that quantum physics is a very strange kind of part of reality, which has been discovered about 100 years ago, and it's in the 80s. Some quantum physicists like Feynman, the famous physicist Richard Feynman, he started thinking about how to use this strange type of physics of little particles to actually do computing that is somehow better than the way we do computing now. And he came up with this idea of replacing the classical bits that we process, the zeros and ones that we process in current computers with what's known as a qubit or a quantum bit. And this is essentially a state of a quantum particle, and like an atom or an electron. And this kind of quantum particles can exist in these strange superposition states, which effectively means that they can at the same time be in several kind of possible states at once in some sense. And so this suggests a potential kind of massive parallelization that potentially could be done if we could exploit this quantum phenomena. And since cryptography, is the security of all cryptography is based on the hardness of computational problems, then this can potentially mean that cryptosystems may be broken much faster if we have practical quantum computers. So, this is the kind of basic idea behind quantum computing. And, you can visualize one of these quantum bits as like a little magnet in a magnetic field. Electrons kind of tend to behave like this, and they are oriented in some way, like here the north faces up. And you can change the orientation by changing the field, the magnetic field that you apply. And you can also put these electrons in this kind of superposition state where, say, some percentage of the possible outcomes, like the north on top has a certain percentage, and the other possibility has another percentage, a kind of probability. And so if you have, two such particles, you could have them in a superposition where all four possible, outcomes have the same weight, or you can have different weights. And in general, if you have, n such qubits, then you could have 2 to the n possible outcomes, and all these 2 to the n outcomes could exist simultaneously in this kind of superposition state. And we can try to do computation on all these 2 to the n or exponentially many states. So it's potentially, looks very promising, but there is a kind of catch in that when we do this quantum processing, at the end, we have to actually extract this information, and we have to make some measurement, some physical measurement. And when we measure, all these probabilities disappear, and we just get one of these possible 2 to the n outcomes. Okay, like here we got south on the top for the left and north on the top for the right. And so the trick for doing quantum computation is to arrange things so that after all this computation, most of the probability, like here 96%, is on the outcome that you are interested in, that is the solution of some problem. And then with very high probability, we will get that when we measure and we've solved our problem. But in order to be able to concentrate this probability on the solution of the problem you're trying to solve, you need to have a very special kind of computational problem. You can't do it for general computational problems. And so the kind of conclusion is that quantum computing can be, give you major speed ups compared to classical computing, but only for certain problems for which it's suitable. And it turns out that those problems for which it's suitable are exactly the ones that we rely on in public key cryptography for security. So in '94, there was a famous paper by Peter Shor, and he gave in this paper some algorithms that can run on a quantum computer, and they give exponential speed ups for exactly the two problems that we need in public key cryptography. So the integer factorization problem that RSA security relies on, this can be broken very quickly in polynomial time on a quantum machine with Shor's algorithm. And the discrete log problem that we need for Diffie-Hellman key exchange also can be broken in polynomial time with a variant of this algorithm. And even worse, it's been extended to work also for elliptic curve discrete log problem, which we use in ECDH, elliptic curve Diffie-Hellman. So all the public key crypto is gone once we have practical quantum computers. And you could also ask what happens to symmetric key crypto? Is that also going to collapse with quantum computers? And the answer is that it's not so bad for symmetric key crypto. So there is some speed ups we can get. This is called Grover's algorithm, but it doesn't give an exponential speed up like Shor. It only gives a polynomial speed up. So effectively, it means that instead of a brute force algorithm, say to do a key search on something like AES symmetric key that takes 2 to the n time if n is the length of the key, then with Grover's quantum algorithm, you can square root that time. So you can do it in 2 to the n over 2. So this is still a significant speed up, but it's not very as significant as an exponential speed up. So many people ask me, why can't we just scale up the length of the keys that we have in RSA and Diffie-Hellman, so that it compensates for this Shor's algorithm, so that they'll be secure against quantum computing. But as I show in this table, you'll have to scale the length of the keys by a kind of sub-exponential or almost exponential factor in the length of the key in order to restore the security of RSA against quantum computing. So basically, it means you'll need terabits of keys to have a secure RSA key. It's not going to work in practice. And on the other hand, for symmetric key crypto, because the speed up is only a square root, it's enough to at most double the length of your symmetric key, say from 128-bit to 256 bits. And your AES 256-bit can still be at least 128-bit secure, even against quantum algorithms. So even with the standard AES 256, we don't really have a problem with, even in the quantum world, with symmetric key crypto. The problem is really with public key crypto. And in practice, even this factor of 2 is probably an overestimate. You can probably scale the key by less than 2 for various reasons. So it's really public key crypto. And you may ask, okay, so how far away are we from this kind of bad future where RSA and Diffie-Hellman will be gone? So to give you some, no one really knows the answer to this question, but to give you some idea, I give here a figure of some recent study on the concrete size of a quantum computer needed to break elliptic curve discrete log with Shor's algorithm. And you can see it requires something like around 2,000 qubits. And the number of quantum operation, these gate operations that are required in the algorithm is about 2 billion, right? So this is the kind of size that we need in order to threaten practical, current public key crypto systems. And you can compare it to the progress in the kind of size of practical quantum computers over the years. So you can see that the recent kind of sizes of quantum computers by IBM and Google, they reach about 100 qubits or so in the latest IBM release. Although IBM is kind of planning to move to the region of 1,000 or more qubits in the next 2 years. So, this is starting to get uncomfortably close to this 2,000 qubits that we are talking about to threaten Diffie-Hellman. Although the other side of it is this large number of gates, which is also a big problem with quantum computing at the moment, is how to do this many gates without noise problems and so on. So it's not clear, how long it will take, but it seems that many people believe that within the next 10 years we'll have a computer that can realistically try to break current public key crypto systems. And so because of this, the community has started to think about mitigations, how to defend against this coming future. Because all this public key crypto that is going to become insecure with quantum computing is in all our web and all the other software that we use. And what attackers could do is they could just record all the ciphertexts we are sending now in our TLS sessions, and then keep them until 10 years time when they have a quantum computer to decrypt them with. And so there needs to be, for many applications, you need actually to keep the secrecy of information that you send today, for many years into the future. Like if you think of sending your, personal health information or things like this, I mean, this should last a lifetime of privacy, whereas here we're talking about 10 years into the future, it may get revealed. So we need to have enough time to upgrade our infrastructure to quantum safe alternatives and to allow time for all the stages of standardization, implementation, and deployment. And then add on to this the time that we need for securing our data. And all this should be smaller than the time to realize these practical quantum computers. So that's why we need to start as soon as possible in this process. And so, as I'll tell you today, there is a lot of progress in producing new cryptographic standards that resist quantum attacks. And so this is the kind of goal of quantum safe cryptography. It's to design kind of plug-in replacements. So these are still going to be public key cryptosystems that run on classical computers, and we can just replace our Diffie-Hellman or RSA implementations with these new algorithms that rely on some new computational problems that we believe resist quantum attacks. And I'll show you different approaches to do this. So this is quantum safe cryptography, and it's also known as post-quantum cryptography or PQC. These are both the same thing, but there is another term which sometimes is confused with quantum safe or post-quantum crypto, and this is quantum cryptography. Okay, you can see it's a very similar name, but there is a very big difference between them. So quantum cryptography is also known as quantum key distribution or QKD. And the main difference is that this technique of quantum cryptography actually uses quantum communication and sometimes quantum computing, even by the legitimate parties that communicate, right? So when you use TLS, currently you don't have a quantum computer to encrypt your ciphertext, but you do need this quantum hardware in quantum key distribution. So quantum key distribution or quantum crypto is very different from quantum safe crypto that I'll focus on today because it needs new technology, whereas quantum safe crypto is just classical algorithms that are secure against quantum future attacks. There is also other problems with quantum cryptography because it doesn't completely solve the problem that public key crypto does. It requires some other means to do quantum safe authentication. So it really only solves the kind of key exchange problem. It doesn't solve the authentication problem. So I won't talk more about quantum crypto in this talk. I'll focus on the quantum safe cryptography approach. All right, so the goal here of quantum safe crypto is to design systems that resist quantum attacks, and we need a public key crypto system. We need a new kind of mathematical computational problems to base this new public key crypto on. And as you know, in public key crypto, there is a very delicate kind of balance when we design these algorithms, because we need, on the one hand, enough math structure that allows us to do this magic of public key crypto, where we encrypt with one key and we decrypt with another key. But on the other hand, we don't want to put too much math structure, because then the attackers come and exploit it to break it, especially with quantum computing. So still, despite this difficulty, there have been a variety of approaches developed to achieve this, as far as we know. And I've listed the main approaches here. So I'll go through each of them and tell you a little bit about them. The main approach which is the great majority of the candidates we have, are based on this idea of adding some noise or errors to some linear equations. And these approaches are called codes and lattice approaches. And the kind of idea comes from error correction codes. So I don't know how many of you are familiar with error correction codes, but they're very commonly used in wireless communication to correct errors that are received. And a very popular way to build these codes is to use some linear equations. So basically, we take our message X that we want to kind of protect against errors, and we multiply it by some matrix A. So this is just a linear combination of the coefficients of this vector X. And then we add some, and then when we use it to protect against errors in communication, the communication channel will introduce some additional noise that we call E. But this noise is somehow small. Maybe it only corrupts, a few of the coordinates of these vectors, or maybe it doesn't have very big numbers in the entries of this vector. So this noise is small in some sense. And if it's small enough, we can use the kind of redundancy that we introduce by this matrix. This matrix kind of expands the size of the vector X into a longer vector A times X. And we can use this redundancy to kind of remove the error and decode the original X from this noisy vector Y. So that's the idea of error correction codes. And in communication, this coding matrix A is chosen to make the decoding of the errors easy. So we can remove the errors in communication. But when we use this in cryptography, we want to make the decoding of the errors hard, right? Because this is going to be the attack problem, which we want to be difficult. We can do this by using a matrix here that is kind of random looking, because random codes are known, in coding theory to be difficult to decode when the dimension of this matrices is big. So that's the kind of idea for the hardness of these codes and lattices that we use. So you can also view it in a geometric way. So you can draw these codes and lattices as kind of a grid of points in some space. So here on the right, I have a two-dimensional example, and these green dots are the code. And then we can extend this kind of definition to higher dimensions than 2. It's not so easy to draw anymore, but mathematically there is no problem to go to any dimension n. And it turns out that solving some kind of geometric problems related to such lattices or codes tends to be quite difficult as we increase this dimension. So basically, for example, if you look at this green grid or lattice, and I ask you, what's the closest grid point to this origin of these two axes, this point here, then it's very easy to see, that it's this point here. You can just look at the picture. But when you get to high dimensions where you can't draw things like this, you need an algorithm to find these short vectors, as we call them, or points that are close to the origin. And this kind of algorithms have to kind of do a kind of brute force search, essentially, which leads to a running time that is exponential in the dimension. So if we use dimensions that are in the order of hundreds or thousands, this running time of the best algorithms we have to solve these lattice problems becomes infeasible. And the nice thing is that this is true even against quantum computers, as far as we know today. Even quantum computers need exponential time to solve this kind of geometric lattice problems. And so this is kind of the basis for lattice-based crypto, is to design a public key encryption so that breaking it requires to solve this kind of hard geometric problems. And so the encryption itself, based on this idea, is similar to what I described before. Basically, you know, to have a public key, you have a kind of description or basis for this lattice. These are these blue vectors that allows you to sample at random any of these green lattice points. And then, you know, to encrypt a message is going to be like a random lattice point here. Let's say this one here. And then to encrypt it, we just add a little noise to it to get to this point X here. And this becomes the ciphertext that we send to the other side. And the other side will have to remove this error and decode this X to the closest grid or lattice point. But in order to decode efficiently, you need to have some secret trapdoor that is the secret key. Without this trapdoor, decoding this error to the closest lattice point is infeasible because it looks like kind of a random code and or lattice, so it's hard. So that's kind of the idea of how lattice-based crypto works. And you know, this approach kind of started you know, in the 1970s. It has its origins with the knapsack cryptosystems that Merkle and Hellman came up with. But at that time, lattices were not very well understood. And, you know, 4 years later, there was a new algorithm called LLL, Lenstra-Lovac. So one of those guys was Scott Contini's PhD supervisor. And this is a very famous algorithm that actually allows you to solve these geometric lattice problems to some approximate degree. But the approximation kind of quality degrades exponentially with the dimension. Now, this kind of approximate solution of LLL was enough to solve Merkle-Hellman and break this. So this is what Shamir did in this time. But so at that time in the 1980s, people tried to fix this Merkle-Hellman system, but they kind of got into a loop of repairing and in a heuristic way, and then breaking again and repairing again, and no one kind of knew how to do this in a secure way, because there were always kind of shortcut attacks that made the system insecure. And so this changed in the middle of the 1990s when you know, there was a breakthrough work by this guy Itai, and together with Dwork, they came up with a new way to build these lattice functions, like one-way functions that came with a security proof. So they showed that, you know, if you can break the one-wayness of these functions efficiently, you can also break kind of the worst case of lattice problems in some sense. And so if you believe that lattice problems are hard in the worst case, then it means that this is a secure way to build lattice crypto. And so this was a breakthrough because it allowed some more scientific way to design this kind of crypto systems to be secure. And this was really the basis for all the developments that have followed over the last 25 years. So at the same time, there was also some new, more efficient lattice systems introduced called Entru, which used a very special type of lattices, which we call structured lattices, that are kind of built with an algebraic or polynomial structure. This allows us to speed up the computations of the algorithms in encryption and decryption, and also reduce the size of the ciphertext and the keys. So this was very practical, but it didn't have any kind of security proof like the Itai theoretical construction. On the other hand, the Itai function was very impractical because it had very long keys. So there was kind of a gap between theory and practice. But over the years, this gap was narrowed, and you know, I list here some of the developments that have led to this. So Michiancio introduced in the 2000s a structured version of ITI's function that was much more efficient. And then Regev introduced a few years later this learning with errors, or LWE problem, that is the basis for public key cryptography that is practical with a security proof. And then some improvements followed for lattice-based signatures using some new techniques for trapdoors and for structured lattices. And finally, I was fortunate enough to also be involved in this research of introducing these structured problems for public key encryption with security proofs that are known as polynomial LWE or ring LWE, together with other researchers that concurrently came up with similar ideas. So once these foundations were laid, in the next decade after this, I may have left this part out. But anyway, in the next decade, there followed more kind of improved efficiency techniques. So this is basically the decade from 2010 to the present. And they improved both the efficiency and also allowed building more kind of powerful types of cryptosystems, such as ID-based encryption and so on, which I'll talk a bit more about later on. So this is kind of the history, and so lattice-based crypto is divided now into this kind of two kind of types or flavors. One is the unstructured, that is based on this LWE problem. So this kind of doesn't have so much algebraic structure, and so it's you can think of it as having a lower security risk because it's less likely that people will come up with attacks that exploit any structure. It's more kind of random. There's algorithms like Frodo-Chem that are based on this kind of problem, but they have quite large, sizes of keys and ciphertext and are quite slow. And then on the other side, you have a structured types of lattice encryption schemes that, as I mentioned, are much more efficient. And as you can see, there are several proposals in this category, and they have quite relatively short keys and ciphertext, and also fast algorithms. So the disadvantage of those is that we are somehow less confident in their security. They have some higher risk, although they've already been studied for over 25 years, and there's not been any serious kind of flaws discovered in terms of security. So these are actually likely to become the new standards, one of those approaches. So just to summarize the performance and security of lattices, the best attack time, even against quantum computing, is kind of exponential in the key length. But because there is a constant there in this exponent, in this big O, and the constant is quite small. So it means we need to increase the key concretely to quite large sizes, of kilobytes, in order to make this sufficiently high security, say 128-bit security. And so as a consequence, the length of the keys is not as short as we would like. It's something like, between 10 and 40 times the length of, ECC keys. But the speed of the algorithms is pretty good and similar to what we have with ECC, and sometimes faster. So this is the kind of performance we get typically with lattice systems. And then we have codes, which, as I mentioned, are using a similar approach of adding noise. But the main difference is that the kind of way that we measure the smallness of this error or noise is a bit different with codes. They use smaller kind of numbers in this code matrix, usually binary matrices. But they have similar kind of security properties. And they are even older than lattices in terms of how they were used in crypto. They were introduced by McAleese in the 1970s. It's one of the first public key systems proposed. But the problem with this scheme is that it's got very long keys, so it's longer than in the hundreds of kilobytes. Even though on the other hand, the ciphertext is really short compared to lattice schemes. So it's kind of like the two extremes of very long keys and very short ciphertext. So the other problem with codes is that it tends to be quite difficult to make digital signatures with codes, unlike lattices, where we can do signatures quite efficiently, as we'll see. So codes are also kind of in the background, but they have several drawbacks in the main. Okay, then what are some of the other approaches to quantum safe crypto? So we have what's known as multivariate nonlinear equations. So all these equations we saw in lattices and codes were linear, but we added some noise to them. But here we actually use nonlinear equations, like quadratic equations and things like this in lots of variables. And we try to hide the message by processing it through such polynomial equations. And then to decrypt with the secret key, we have some trapdoor that is hidden in this nonlinear system that kind of transforms it into an easy to solve system, like a linear system. And the problem is that, putting in this trapdoor that makes it easy to decrypt with the secret key can make the attack problem on these systems, much easier than it would otherwise be. And so the security of this kind of systems is not easy to analyze. They don't have this kind of security proofs that we have in lattice crypto and coding crypto. And so it's not so clear how to relate the security of the crypto system to hard problems like solving nonlinear equations in general. And even today, one of the recent candidates in the NIST standardization process I'll mention next has been broken because of this misunderstood security of multivariate equations. But on the bright side, in terms of performance, these systems can have really short signatures, and the algorithms are also quite fast, although the keys are also quite long. So this part is similar to the codes kind of approaches. All right, what else can we do? Another way that researchers have tried is to kind of use the ideas from elliptic curve cryptography that's been used for a long time. But as I mentioned, the classical Diffie-Hellman based ECC is not quantum secure. And it turns out that the basic mathematical reason for this is that, the group on elliptic curves that is used in ECC is commutative. So we can do, multiplications A times B is the same as B times A. But this makes it easy for quantum computers to break this discrete log problem. Also, researchers tried to find other structures in elliptic curves that don't have this commutativity. And they found this, what's known as isogenies. And these are kind of functions that you can use to go from one elliptic curve to another one. And these functions themselves, we can compose with each other in order to define a new mathematical structure that is non-commutative, because composing functions is not commutative by its nature in general. And so there are Diffie-Hellman-like kind of non-commutative protocols that are based on this idea of isogenies. And these are very interesting protocols, but they are relatively new, only studied seriously in the last 20 years or so, or even less. And also in terms of performance, they tend to be quite slow. although they do have an advantage in terms of the length of the keys in ciphertext. So the lengths are only about, twice as long as the classical ECC kind of lengths. So this is another interesting approach. And finally, if you only want to produce a digital signature for authentication rather than public encryption, then you have other options, because it turns out you can build digital signatures, without the full power of public key crypto. You can actually use symmetric key crypto in some way to build digital signatures. And this is a very old idea that came from the one-time signatures in the original Diffie and Hellman paper, these Lamport signatures that they described. So these are signatures that you can only use one time, and then you need, if you want to sign another message, you have to produce a new key. But it turns out you can, combine a lot of one-time signatures by hashing them, taking all these keys of one-time signatures and hashing them together with a hash function into arranged in a kind of tree form, or Merkle tree, as we call it. And then you publish as your public key this Merkle hash of all these one-time keys. And then every time you want to sign a message, you just use one of these keys, one of these one-time keys to sign that message, and you kind of give a path in this tree to allow a verifier to check that this key is really registered inside this hash. So it's possible to do signatures, and there is an algorithm called Sphinx that is one of the quantum safe signature proposals that uses this approach, but it has relatively long signatures because of having to use this kind of tree structure. And there's also other approaches, like an algorithm called Picnic that uses symmetric key crypto to build signatures, but in a different way. It uses what's known as zero knowledge proofs for circuits to do the signing, rather than using this Merkle tree idea. But again, it produces relatively long signatures. So the advantage of these approaches is that in terms of security, we have very good confidence in them, even more than lattice schemes or all these other things, because we just rely on the good old symmetric key systems like AES. But on the other hand, they are relatively inefficient in terms of length and sometimes speed. So this is kind of the trade-off that we have with this kind of approaches. So you can see that there's a variety of approaches, and so the need, in order to make these things practical, people realize that we need new standards, right? Because all the crypto that we use today is specified in standards so that everyone can agree and use it. And so NIST in the US that maintains all the big standards like AES in crypto, they decided to initiate this new standardization process for post-quantum crypto, or PQC process. And this happened, this started a few years ago in 2017. They made a call for algorithms for encryption and public key encryption and digital signatures that are quantum safe. And there were about 70 algorithms submitted. I also submitted an algorithm, and all these algorithms were then subjected to a lot of analysis and evaluation over the last 5 years. And so here we are now in the third round. And any day now, NIST is going to announce the final standards for the new quantum safe public key crypto standards, and hopefully by in another 2 years or so we can start to deploy them in practice. So over the years, years of this process, there's been a lot of security analysis by the research community of all these proposals. Many of these were broken, and I also had some fun to break some of those. which I quite enjoyed the fact that I was able to find an attack that decrypted the ciphertext faster than the legitimate decryption algorithm that had the secret key. So that was an amusing thing. You know, even in the last round, there's been some recent cryptanalysis of this rainbow signature scheme. So, you know, the analysis is still continuing, but, you know, we have established some schemes that are quite, they look quite solid. So, you know, this process has looked at both security levels, you know, they have a range of levels, you know, from level 1 that is equivalent to AES 128 to level 5 that is AES 256 level. And of course, they also looked at performance aspects and you know, other implementation related things like how easy it is to make them resistant against side channel attacks, which reveal information to an attacker based on things like the running time of the algorithm. So to give you an idea of some of the, you know, the performance characteristics, you can see on this graph, you know, the public key size versus ciphertext size for some of a range of these candidates in round 2. And you can see they are labeled by the different approaches. So you can see that isogeny systems are over here with a very small ciphertext and public key sizes. Whereas you know, the structured lattices in green are somewhere in the middle. And then we have, you know, the McAleese with its very extremely large public key, but very short ciphertext on this corner. And you have unstructured lattices here with both ciphertext and public keys quite big. So and you can also see the coding, some other coding schemes that are somewhere in the middle there. So this is kind of situation with respect to sizes. And you can also see on this graph the speed of these algorithms. And again, you can see all these green points are the structured lattices that are relatively fast and relatively short, moderately short. You know, again, there are some isogeny systems that are much slower despite having this short length. And then McAleese is over here on the top corner. It has both large public keys and also large running times. So a similar kind of comparison can be done for the signature schemes. So this is what we have here. But you can see that for signature schemes, there's many fewer options that we have. Eventually, we have much fewer options in this case. And you can see that the symmetric key systems, you know, have large lengths, but for signatures, but short lengths for the public key. The lattices are somewhere in the middle, and the multivariate systems, yeah, have short signatures but long keys. So you can see a range of behaviors for the different approaches, which is why there is no, you know, there is no one single best choice here. It's kind of a trade-off between different.
Nic, mamo, nieważne. No. Nic, po prostu dokumenty.
All right, so so here on this slide, I have a list of you know, the finalists of this round 3 of this NIST process. So you can see that for public key encryption, you know, the 3 of the 4 finalists are based on structured lattices because they have this kind of reasonable trade-off for all parameters, whereas we also have McAleese with this kind of extreme mix of trade-offs. And then we have a range of alternatives that are based on codes and also isogenies and also some unstructured and structured lattice. So these alternates are kind of kept as kind of backups in case something unexpected happens for the security of these finalists. But most likely the finalists, one of the finalists, what NIST intends to do, according to what they said, is that they will pick one of these structured lattice schemes as the actual standard, and then they may pick one from, they may pick also McAleese as a kind of alternative because it's based on a different kind of problem. And yeah, it's not clear what they will do with the alternates. They may have a fourth round that will kind of continue to evaluate those. And then for signature schemes, you can see there's two structured lattice candidates, the Lithium and Falcon. So again, one of those probably will be chosen as the standard. And then they wanted to have Rainbow as an alternative, but Rainbow had this recent security attacks, so it may not make it eventually. And as alternates, they have some symmetric key variants that I mentioned and another multivariate scheme. But this multivariate scheme also had some security issues, and so it's not looking likely that it will get through. But yeah, to give you some better idea of the performance of these different finalists, I have this table here, and you can see that the structured lattice systems are fairly similar in performance. So they have lengths in the order of 800 to 1 bytes to 1 kilobyte, but the time of the running time is very fast. This is in thousands of cycles on a Intel chip. And then McAleese, as we said, has very short ciphertext. It's almost in the level of ECC, but the public key is huge, 260K. And also, yeah, the time for decryption is also relatively slow. And then for signatures, you can see the two structured lattice schemes also are in the order of 1 to 2 kilobytes for lengths, whereas Rainbow has this extreme behavior of very huge public key and very short signatures. All right, so I hope this gives you some idea of what the performance and the characteristics of these things are. So currently the status is that we are waiting to hear NIST's final decision for this standard. There's been some recent cryptanalysis by the Israel Defense Force on some of these lattice systems that optimize some of the attacks by a few bits of security, but there's no kind of major new ideas in there, so it's not likely to make a huge difference. So it's likely that we'll end up with one of these structured lattice schemes as a new standard. Okay, I wanted to mention also some other standard efforts. So the European Telecommunications Standard Institute, or ETSI, has also a working group on quantum safe crypto. And they also have some recommendations for standards for quantum safe primitives, and they even specify some other things like types of public encryption that are called identity-based encryption with a hierarchy. So these are kind of encryption where the public key can be any string, like an email address. And so you don't need to fetch a public key in order to encrypt to someone. You can just use the identity string for whoever it is, and then that person with this identity string can get a decryption key for that identity from some authority that can generate keys, private keys. And this kind of encryption can be used in various applications. And there is the standard called Latte based on this. So I also wanted to mention a bit about implementation issues. So this, you may know that implementing securely and well public key crypto, or even any crypto, is a non-trivial task, because on the one hand you want to get high performance for these algorithms, but on the other hand you have to watch out for all sorts of attacks, like side channel attacks that can leak information to the attacker. So an attacker that can measure how long it takes for you to decrypt a ciphertext might be able to deduce something about your secret key. So it's important to protect against this kind of side channel attacks. And so achieving both the high performance and this kind of side channel protection is a non-trivial task, and there is a lot of work in the research community on this. So, for example, one of the main algorithms that are used in structured lattice systems are algorithms to do fast arithmetic for polynomials, because this structure is related to polynomials. And so we work with kind of polynomials, or polynomial rings as we call them, that we need to efficiently multiply polynomials. And for this, we need to use some fast algorithms, like those that are based on fast Fourier transforms. In crypto, they are called number theoretic transforms, or NTTs. And so they also involve special choices of these parameters, this modulus Q and so on. So this kind of fast algorithms are a main area of interest in doing fast lattice crypto. And one difference from the kind of traditional public key crypto is that we use modular arithmetic, but we use quite small moduluses, in the order of 10 to 20 bits, rather than hundreds of bits or thousands of bits as we use in RSA or things like this. So that's part of the reason why we can get quite fast performance with lattice crypto. And another kind of interesting aspect of implementing these systems is that because we need to have this small noise or errors for security of these systems, we need to kind of have efficient algorithms that can sample these small errors from the desired probability distributions. And in lattice crypto, we often use this kind of bell-shaped distributions or Gaussian distributions, but they have to be discretized, so we can sample integers with these distributions. So I've got some pictures of these distributions here, and we can sample them either on integers or even on higher dimensional lattices, depending on the application. And so there's a lot of research has gone into devising efficient implementations and algorithms for this that are also a constant time to defend against side channel attacks. And I've also worked on this with my students, and I have here on the bottom right some results from one of our algorithms to do this kind of sampling efficiently. This is joint work with my student and my colleagues at Monash. So this is another important aspect. And then in terms of deployment of this quantum safe crypto, there is already a number of software libraries that implement it, so they can start to be used. So there is a project called Open Quantum Safe, or OQS, and this has a whole library of these NIST algorithms. This is called libOQS. And they also have a kind of variants of the OpenSSH and OpenSSL that integrate these quantum safe algorithms. So you can actually run SSL with those. And there's also a bunch of other libraries there are some libraries that have been optimized for embedded processors, these ARM Cortex processors, M4. And this is another work that I've been doing with my students and colleagues on evaluating and adapting Wolf SSL, which is another TLS library that is especially optimized for embedded processors, and making it integrating quantum safe algorithms into those. So we've got some evaluation results on those. And we're also working with the Bouncy Castle library. So this is an Australian well-known software library for crypto, and Bouncy Castle is also upgrading their crypto to quantum safe, and we are working with them to implement some of these NIST lattice-based algorithms. So this will appear soon as well. So in terms of research, I've listed some of the main kind of topics that we do. So me and my group at Monash, and also the other research community in cryptography. So now that we have kind of these candidates for quantum safe crypto, we still have to continue to study, their security foundations against quantum computing. How secure are these systems really against quantum computing? Have we missed some aspects that might allow some quantum attacks to break these things? So this is something that we are working on as well. Another thing that we're working on, as I mentioned, is the efficient implementation techniques for these systems, and especially when it comes to more advanced kind of post-quantum systems that I'll mention in a few slides. The implementation becomes even more important because these more advanced systems require more complex algorithms, and it's even more important to have them run efficiently and with a short length, especially with lattice algorithms. When we come to advanced protocols, for example, I'll talk about privacy preserving blockchain transactions. And in this case, we need protocols called zero knowledge proofs that are using lattices. And in those cases, the length of these proofs tends to increase even more compared to the length of just public key encryption or signatures. And so we had to devise some new kind of techniques to improve the design of these systems to make them more practical and shorter. So I'll give you two examples of some of this recent research to give you a taste of this. So the first one is related to this ID-based encryption that I mentioned before, or hierarchical ID-based encryption. So as I mentioned, this European Standards Organization proposed the recommendation standard for this type of ID-based encryption, and it's actually being considered by the United Kingdom government for their emergency communication network, because it's very easy for emergency, apparently, situations to use this ID-based encryption, because they don't need to worry about this kind of certificates that are involved with traditional public key encryption. But on the other hand, this kind of special public ID-based encryption, it requires this more advanced kind of lattice sampling algorithms. It's a kind of extension of the Falcon signature that I mentioned in the NIST process. And so the running time becomes even more of an issue. And in the ETSI standard, they estimated it would take a few minutes to run one of these key delegation algorithms. And also they have relatively long keys and ciphertexts. And so with my student and colleagues, we have a very recent work on this that we just put it online last week. we have an improved version of this latte system, and we have improvements on both the design aspects and also the implementation. So in terms of design, we have optimized the dimension of the lattices. We managed to change the design a bit to reduce the dimension so that we can reduce the length of keys and ciphertexts and also speed it up. But also in terms of implementation, we have kind of applied this kind of techniques that we developed for this Gaussian error sampling that I mentioned before to speed up this algorithm. And we also improved some of the kind of Fourier-based sampling algorithms that are used in this key delegation. And we also analyzed the security of how the security depends on the precision of the arithmetic that we use, because this kind of algorithms require floating point arithmetic. And it turns out that sometimes double precision is not enough for security, and you need larger. So you need to quantify how the precision affects security so that you can choose the right amount and not too big so that it's not too slow. So overall, we were able to speed up the delegation time. So previously it was estimated in the order of minutes, but now we can do it in under a second. And we've also shortened, the length of decryption keys by several times, and ciphertexts are slightly shorter as well. So, this table shows a summary of the lengths of the parameters of our improved latte versus the original for different security levels. And you can see that, for example, in terms of private key lengths, you can see this factor of 3 improvement versus the original latte, but it's still, the length is, so this length is in bytes, so it's 6 kilobytes versus 19, which was the original, but it's still, several times bigger than what I showed you before for the, just plain public key encryption, which only needs, in the order of a kilobyte. Here we need in the order of 6 kilobytes or 3 kilobytes. So there is some overhead because it's a more powerful kind of hierarchical identity-based encryption. But it's much more practical than the previous parameters of the original latte. So this is, this kind of efficiency improvements for these more advanced type of systems is one area that research is working on. And another example of this that I'll show you now is to do with blockchain transaction protocols that protect the confidentiality of transaction information. So the motivation for this is what I show on this page. So if you look at traditional cryptocurrencies like Bitcoin, they don't really aim to protect the privacy of the amounts that are being transacted or the identities of the sender and recipient. This can all be traced on the public blockchain. But on the other hand, it allows the blockchain to work safely, because it means that the verifier can see all the amounts and be able to check that the balance of the accounts is preserved, so that that people are not spending money that they don't have. But what if we want to hide these amounts and identities to protect the privacy of these transacting parties? The problem is, we can encrypt those amounts that are being paid and the identities, but then how is the blockchain going to verify that the spender is not overspending their account, because the blockchain cannot see the amounts anymore? And so what the solution that was adopted in some kind of private cryptocurrencies like Monero, that is based on this ring confidential transaction or ring CT protocol. The idea was to allow to encrypt these kind of amounts being transacted and the identities, but instead of the verifier just doing the checks in plain form, the spender actually attaches what's known as a zero knowledge proof. And this is a kind of cryptographic protocol that, is able to prove to a verifier that whatever is encrypted in this commitment or encryption of the amounts is not overspending the amount encrypted inside the accounts of this spender. So a zero knowledge proof allows a verifier to check a statement without making the prover to reveal the secrets, which are in this case the amounts and the identities. In fact, to hide the identities, we use a variant of such zero knowledge proof called a ring signature. And the idea here is that when the spender spends, so let's say the spender is Alice, when Alice is spending, she's going to take some, she's going to sign the transaction, but when she signs, she's going to sign together with the public keys of other users in such a way that when the verifier checks the signature, is also checking it together with the other public keys. And the signature just proves that it's a signature, it's a valid signature by one of these public keys that Alice used, but without revealing which one. So in that way, the anonymity of Alice is preserved within this group of public keys that were used in this rig signature. So this is how the anonymous or the identity of the signer is protected. So both a ring signature and a zero knowledge proof to check the balance are needed in this ring CT. Now, ring CT itself is implemented in Monero with non-quantum safe techniques, the discrete log ECC-based crypto. So I have a bit of details on how it works, but I don't think I'll go through this. But the point is that it's using some discrete log-based non-quantum safe techniques to do these zero knowledge proofs and ring signatures. And so what we did is we tried to convert this ring CT protocol to be quantum safe by implementing it with lattice-based crypto. And it turns out that it's not straightforward to do this efficiently in a direct way, because if you do it in a kind of naive way, then the lengths of this all these zero knowledge proofs and ring signatures, they really blow up to megabytes. And so we really had to focus on each of these components and see how we can find some new techniques to optimize, really use the properties of these structured lattices, some of the mathematical properties of these polynomials underlying these zero knowledge proofs to really kind of compress the length of these proofs, zero knowledge proofs and signatures, in order to make them more practical. And so that's essentially our result is a much improved efficiency for a quantum safe version of ring CT that we call metricity. And in fact, we have two versions of this protocol. One is called metricity that was our first attempt in 2019, and then so last year we came up with an improved version called Metricity Plus, and this is actually going to be published or presented in the Security and Privacy Conference this month, later this month. So just to give you some idea of what we could do with this with all our improvements. I have these tables here. So here we show the length of the proofs that we have in our original metricity protocol and our improved metricity plus. And then we have another improvement, which we call compression, which is kind of an adaptation of some other earlier work in other types of signatures. But you can see that we can get down to sizes of proofs. This is in kilobytes, so we can get down from over 100 kilobytes to only a few tens of kilobytes. The length of public keys is only a few kilobytes. So this is the lengths of transactions that we have in this quantum safe protocol. And here we have some of the running time performance of the different algorithms. So, the main bottleneck is the generation of transactions by doing all these zero knowledge proofs. So you can see that this kind of running time in milliseconds, it can be done in less than half a second, even with a large anonymity level. So the anonymity level here is the number of kind of public keys that we use to hide the sender or the sender's identity. So it's quite practical already. And actually, we are in the process of looking for some industry partners to help us to look for commercialization opportunities for this kind of technique. So yeah, if any of you know of any such potential partners, then you're welcome to contact me and we can discuss further. So yeah, that's really all for my talk today. So thank you very much for joining me, and I'm happy to answer any questions. By the way, I wanted to add here some more references. If people are interested, I can also send the slides. I haven't added the references yet, but I can send you later maybe an updated version.
Yeah, that would be great if you could provide the slides. We can link to it from the meetup page. So that would be, and any references you want to add. So thank you so much, Professor Steinfeld, for this overview. We have less than 10 minutes left. So if people have some quick questions or discussion points, fire away. And feel free to use the chat if you want to, or otherwise just go ahead and speak.
That was very good. Thanks, Ron. Honestly, I had a lot of questions on the way when you were presenting, but I could kind of got lots of answers when you were going ahead. So that's great. Thanks a lot.
Oh yeah, no, nice to see you, Sarah.
Yeah, exactly. Nice to see you too.
Yeah, I'm glad that you got something out of it.
Yeah, definitely.
So
thanks for doing the presentation, Ron. I really enjoyed it. I'm not a cryptographer. I don't understand a lot of this, but I'm glad that I have some acronyms I can take away and pretend I know what I'm talking about. At least I know what a release candidate is.
Yeah.
So how soon are we looking for these candidates to be part of like TLS? Is it could be TLS 1.3, or is they going to upgrade to a new protocol? Any thoughts on that, Ron?
Yeah, I'm not actually sure how TLS will handle this, but I guess it will be a new version. Yeah, maybe 1.4. I don't know. I'm not sure. Yeah, that's a good question. So yeah, because when we did this evaluation with the, I mentioned, with the embedded versions of these quantum safe algorithms, yeah, we did a kind of ad hoc variant of TLS 1.3 that was implemented in Wolf SSL, but yeah, I don't know how it will be handled formally.
Any other questions before we finish up?
I have a question.
Yeah.
Well, the presentation was very good, so thank you. But I'm very curious about what you think about what network latency looks like early on, post us finding, well, relatively efficient algorithms. Do you think there's going to be a drop in network latencies? Well, not a drop, but increase in network latencies. And what do you think that makes the user experience like with the internet? Do you think there's going to be a shift in how people use the internet for some amount of time?
Yeah, that's a good question. I mean, so there's been some evaluations of TLS with these quantum safe algorithms with their longer, ciphertext lengths and key lengths, and the conclusion that was based on using in the studies that I saw, the conclusion was mostly based on typical network latencies. The overhead due to the quantum safe algorithms was not significant compared to the already existing network latency. So based on these studies, I would say that it may not make a huge difference, but yeah, I mean, I guess, yeah, maybe if networks keep improving their latency times, then it may become more of an issue. But one thing that I know is an issue is that because these ciphertext sizes are bigger, some implementations of TLS they were designed with relatively to work with short IP packet sizes, and when you try to, there are somewhere in the protocol stack, there are some limit in these implementations on the size of the packets you can use. And so some people that tried to use them with these larger ciphertexts of quantum safe, they hit some problems there. And that's one of the reasons why I think the NIST was quite they really looked for systems with relatively short communication sizes, because it could cause some problems with existing protocols that are used to much smaller sizes. So I mean, I don't know if it's really a big issue in terms of performance, but in terms of kind of the existing infrastructure, there are all sorts of limits that in practice cause problems. So yeah, but I think with the finalists that we have, probably these issues are not a big problem, because the ciphertexts are sufficiently small to fit within the existing limits. Yeah.
I guess a follow-up question to that. Do you know if, for example, NIST has any protocol to roll out this new post-quantum crypto? Because I know in the case of like TLS 1.2 and 1.3, many sites are using 1.2 still, even though 1.3 is available. And I guess in the case of crypto, like they can do a hard fork or whatever they really want to do, because they have complete control of the network. But does NIST like have any standards around how quickly people should be rolling this out, I guess 10 years from now?
Yeah, no, I don't think they have that yet, but actually I just heard a few days ago that that the White House released a statement for all US government agencies with quite a detailed timeline plan for migrating to quantum safe crypto. And it's really, it looked to me that it's quite a short timeline, like within a couple of years. I think they want to have a lot of progress on this in the US government at least. So yeah, looks like it may happen much sooner than 10 years.
Right.
That's
Oh,
amazing.
thanks for answering my questions.
Yeah. Thank you very much. I think we're out of time, but thank you so much, Professor Steinfeld, for coming and presenting today. This is really good stuff. Thank you, everybody, for coming. It's necessary knowledge. You're going to be ahead of your colleagues for being here and understanding what's going to be happening. It looks like fairly soon, and it's good to have that knowledge. Thank you so much.
Yeah, thank you for having me. Yeah, I was very happy to join you today.
Thank you.
Thank you all. Okay, I'm going to end the meeting. Thanks again, everybody, and we'll announce the next meeting in the next week or so. So keep an eye on the AppSec Australia website. Thank you all. Bye-bye.
All right, bye-bye.